This video is intended to give an insight into the status of task 5.12, driver monitoring and distraction detection using AI. We will next highlight our approach to smartphone-based distraction detection. We see that distraction has a high influence on traffic accidents. A first step to reduce this risk is to detect the driver's distraction state. We found that a very simple approach is to use already available sensors, such as these in smartphones. With that in mind, we planned our software-hardware setup. The base software architecture features a smartphone app as a main component, allowing for data recording, for example, emo data, and the application of an AI model to the recorded data. The recorded data can be stored locally or in a server-side data warehouse. This allows for an analysis of historical data in the server-side AI backend. New AI models and app events can be exchanged between the smartphone app and the AI backend via real-time cloud database. We use an app prototype to record emo data from smartphones. In order to train and validate an AI model, we define different simplified attention and distraction states. These states, called labels, are recorded by a second smartphone, logging the state transitions. The data from both devices are then exported as local files. Those files are then loaded into and edited in Python. Next, both files are aligned and combined. This produces nearly 200,000 data rows, which can be visualized as a line plot with colored background. The lines represent the sensor data. The background color represents the smartphone-induced state of the driver, attention or distraction. This data is then used to train a deep neural network AI model. Based on the recorded emo data, this model is supposed to identify the current smartphone-induced state of the driver, attention or distraction. It consists of different input layers, an LSTM layer, which is a very effective type of layer for our purpose, besides others. The model is then trained by using parts of the recorded data. The rest of the recorded data is used to evaluate the model. The line plot shows the emo data. The background color represents the smartphone-induced state of the driver, attention or distraction. The background color above the baseline represents the recorded state during the data collection. The background color underneath the baseline represents the model's prediction. The model reaches an accuracy of 94%. In order to extend the current prototype, the label recording could be automated and, if possible, combined with alternative approaches. Auto-labeling could be approached in two ways: by extensive logging of smartphone data and by using image recognition. Also, the possibilities of complementing the current approach by using image recognition will be explored. The software at hand can detect blinks, yarns, a drowsiness level, and a distraction level. This allows for multiple possible extensions, which will be explored in the future.